biochemical perspective, starting from a patient and drilling down to the DNA. I'm sort of going to go the other way and start from the DNA and expand up to, I hope, to a patient. So I'm going to talk about good versus evil DNA repair because my interest is DNA repair. Obviously, I run the DNA repair group, but in particular in B cells and in B cell cancers. So we can go to the next slide, please. Yeah. So B cells are white blood cells and they make antibodies, and obviously antibodies are vitally important for protecting you from disease. And antibodies are so important, if you can't make antibodies, you're a bubble boy in a plastic bag being isolated from the outside world for your whole life. So they're critical for our defence against infections. And the really clever thing about antibodies is that you have the capacity to make 10 to the power of 15 different antibodies. At any given time, you only make about 1 million different antibodies, or 10 million different antibodies, or even 100 million different antibodies. Those are very big numbers. You don't have anything like 100 million genes in your body to make 100 million different antibodies. Each gene essentially makes just one protein, more or less. So the way you make millions of antibodies to defend you against the millions of infections that you may or may not encounter is that you mutate your antibody genes at very high rates. And you mutate your antibody genes in 2 phases of your life. And so that's a picture of an antibody up there, which is basically a Y-shaped molecule. Not that it really matters much. And the heads of the Y are the parts of the antibody that actually bind to and recognise an infectious organism. And then the stem of the Y is the part of the antibody that then engages the rest of the immune system to come along and kill the infectious organism once it's been tagged with an antibody. So you can make millions of different antibodies because you mutate your antibody genes. And in childhood especially, in the bone marrow, when B cells are developing in the bone marrow, you rearrange fragments of antibody genes to make a whole new array of antibody genes. Kind of like getting a pack of cards and running it through a bandsaw and just randomly distributing the segments of the cards through the genome, and then picking fragments of those cards and splicing them back together with skin tape. And each B cell does that and reassembles its own unique playing card. And that playing card that B cell has for life, and that's the antibody it's going to make. And it's different from every other playing card that every other antibody producing cell produces. And that happens mostly in your childhood, but it goes on during your life. But that process can go wrong, because cutting and splicing DNA is actually a very dangerous thing to do. And we do it because we need an immune system, it's incredibly important. But it has a risk, because cutting and splicing DNA has a small chance of causing DNA to rejoin in the wrong way. And this is a primary cause of cancer, it's called a translocation. So a lot of childhood leukemias are actually caused by this gene rearrangement process. But in adults, that's not such a problem. And most of those childhood cancers are now pretty curable. But in adults, there's another wave of gene mutation that goes on in antibody genes. If we can move on to the next slide. And that's a process called harmonization. And whenever you get an infection, when your lymph nodes swell up, one of the things that's going on in those lymph nodes is that the B cells that are making useful antibodies start to proliferate like mad, they divide and exponentially grow. And at the same time that they do that, it didn't occur to me that I wouldn't have a pointer around the slides here. At the same time that they do that, they actually mutate their antibodies. And essentially it's Darwinian evolution on speed. So the cells that are making a useful antibody start to mutate their antibody genes at an incredible rate. Most of those mutations are bad, but then the B cells compete with each other to see who makes the best antibody by fighting with each other for resources, which is the infection that's causing the stimulation in the first place. And the best B cells win, and the B cells that aren't effective die off. And this goes on over and over again, over a period of days. And it occurs very quickly. My lab has shown that this cell cycle, this replication process, takes a mere 6.5 hours for the cells to go through one cycle of mutation and replication and division. And that's a great thing. That produces antibodies that are 1 million-fold more effective in the space of a few days. So I've been fascinated by this process for decades now. It's really what got me into this process. But if we can go on to the next slide. The bad thing about antibody harmonization is it's critical for making effective antibodies. And if you can't hypermutate your antibody genes, you're actually in trouble. But the downside is if you get certain chronic infections, and the classic, or now classic infection example of this is Plasmodium or malaria, that these chronic infections can cause your B cells to just keep on going through this hypermutation process more or less indefinitely. And if you mutate, unfortunately the machinery that mutates antibody genes, there's a key enzyme called AID, which is probably been mentioned on this slide somewhere. This enzyme AID, it mutates mutates antibody genes, but like everything in biology, it's not perfectly targeted to the antibody genes, and it also mutates other genes at very low rates. But if you proliferate long enough and indefinitely enough, then eventually those mutations in other off-target genes, as we call them, could become critical inducers of cancer. And it turns out that there was a key paper that came out in an international journal, Cell, about 3 years ago, that showed that malaria can induce these B-cell cancers that are called Burkitt's lymphoma, and that the AID antibody mutation process is absolutely critical in producing this Burkitt's lymphoma. So B-cell lymphomas are not particularly common, but they're invariably very nasty. And in fact, it's especially adult B-cell lymphomas. And so Burkitt's lymphoma, and to a lesser extent multiple myeloma, which a lot of you may have heard of, this antibody mutation process is a key contributor. This off-target mutation is a key, and I have to emphasize that the off-target mutation is a key contributor to these cancers, which up until recently were very difficult to cure. Now there are better treatments, but they're still very nasty. We go to the next slide. So, I'm sorry, that's what that slide is meant to show. I'm sorry, the chronic PARP mutation causes these cancers. So, on to the next one. So, I was interested in trying to work out why antibody mutation is able to mutate antibody genes and why it's able to mutate cancer genes. Because what AID does is it enzymatically, deliberately introduces a very minor form of DNA damage into its target genes. And what would normally happen is that damage would be repaired by enzymes that everybody has in every cell in their body that repair damage to DNA every day. Because DNA gets damaged all the time, it's totally normal, and you repair that damage every day in a totally normal way. But for some reason, the damage that DNA that is introduced by AID is not repaired properly. It recruits repair pathways that should repair it. And in fact, there's two pathways that are repaired, and it doesn't matter what they're called. One's called base excision repair, and one's called mismatch repair. And they're both capable of repairing the damage that AID causes. And they both do repair it, but at the same time, they also make the damage worse. So it's a lottery whether these enzymes are going to come along and fix the damage or actually make it worse. And making it worse is a good thing in your antibody genes because it diversifies all the antibodies you can make in a lottery process. But if it goes onto off-target genes, then it's a bad thing. So I was very interested in knowing what determines good DNA repair versus bad DNA repair. How do we tell the difference? How can we predict what's going to happen? So go on to the next slide. And the next one. So I thought the critical thing, something I thought about for a long time, was actually the cell replication cycle itself might be a critical determinant of this. So the whole time that these cells are going around and around in circles, proliferating and mutating, they have to move through a very programmed sequence of events which tells them, I'm going to prepare to replicate my DNA, I'm going to replicate my DNA, and then I'm going to divide in half when I know that I've replicated the DNA and that everything's okay. But these B cells are going through this process on speed. They're doing it far faster than normal cells would do that process. So it occurred to me that maybe what's going on here is that essentially the DNA repair processes in the cell cycle are getting out of sync, and the DNA repair is occurring at the wrong time. So if you go to the next slide, the question is, how do we go about asking questions about such a difficult thing to examine? I mean, historically, when people wanted to look at how the cell cycle works, they would stop cells from cycling and then start them up again. But antibody mutation occurs inside of a human or an animal body. We use mouse models mostly. But you can't stop and start cell division inside of an animal. It's just not possible. So we had to develop tools to ask questions about this. So if you go on to the next slide. So the tool we developed was a thing that I now call deadlock fusion. And so what you see on the right are some cells that have been labelled with two different recombinant DNA constructs. And one of those constructs, stop cycling, but okay. One of those constructs, it's supposed to be on a loop, never mind. One of those constructs makes the cells red when they're in a particular phase of the cell cycle. And the other construct makes the cells green when they're in another phase of the cell cycle. So when they're synthesizing DNA, they're green. When they've finished synthesizing DNA and are preparing to synthesize DNA, they're red. And what we did with those constructs is we then fused those sequences, they're called dead bonds, and they restrict expression of any protein of interest to very tightly defined phases of the cell cycle, mutually exclusive phases of the cell cycle. And we fused those proteins to a special inhibitor which actually inhibits particular DNA repair pathway. And what that meant was that we could inhibit a DNA repair pathway in opposite phases of the cell cycle with exquisite control, without interrupting the ability of the cells to divide, without interrupting the cell cycle itself. That seems like a very esoteric concept, why we don't care about that. But it actually gives us an ability to really look with fine details going inside those cells. And it also gives us the ability in the future to develop drugs that could be targeted to phases of the cell cycle with the same level of exquisite precision. So if we go to the next slide, what we did with those tools is essentially show, and I won't show all the data because there's rings of it, there was a very talented PhD student who did this work, and basically what he showed was that when DNA damage occurs to antibody genes because of this AID mutatory enzyme, that the DNA repair pathways are recruited in essentially the wrong phase of the cell cycle. So these DNA repair pathways would normally be active in the green phase of the cell cycle when DNA is being synthesized, and they carry out very high fidelity repair in that phase of the cell cycle. And that's what we showed, that when we restrict that DNA repair pathway to the synthesis phase of the cell cycle, it gives beautiful high fidelity repair. But when that DNA repair pathway is acting in the wrong phase of the cell cycle, it now causes the AID-induced DNA damage to be made even worse, and they spread the mutations around the gene. So this demonstrated that in fact the reason antibody mutation happens is because DNA repair is recruited essentially in the wrong phase of the cell cycle. So, a paper has just come out that follows on that from our work, or follows on the same field, not follows on from our work, which has shown that when these chronic infections occur and antibody gene mutations turned on for a very long period of time, and you get this mutation in cancer-causing genes, that one of the target genes that's hit by this mutation process is in fact the telomeres on the ends of DNA, on the ends of chromosomes. The chromosomes are like shoelaces. They're very long, but they have ends, and those ends have to be protected with little caps called telomeres. And if those caps on the ends of chromosomes are damaged, in the same way the cap comes off your shoelace, the chromosome will literally fray, just like a shoelace. It will start to unravel from the end, and you end up losing the entire chromosome. So mutation of telomeres is a particularly dangerous thing to happen. It turns out, it's now been discovered just last year, that this antibody mutation process can actually attack the ends of chromosomes in cancer cells. And that actually, if we move to the next slide, gives us, as a surprising outcome of all this work, a potential therapy for B-cell cancers that still have this mutation process ongoing. A lot of adult B-cell cancers where this mutation process is being involved in the development of the cancer, the mutation process is ongoing as the cancer exists in the patient and expands. And what we now know is that in those patients, there's a very high chance that this mutation process is actually attacking their telomeres. And that means from our data, we can predict that if we block DNA repair in the precise phases of the cell cycle that our existing data suggests will have outcomes, then there's a good chance that we can actually specifically kill AID-positive B-cell cancers by making their telomeres fall apart, by preventing those telomeres from being repaired. Now, we haven't tested this yet. That's what we have a grant in place with the NHMRC this year that we just got reviewed back on. It's very positive. So we're hoping that next year we'll be able to start in collaboration with researchers at Westmead to test this theory out, that can we kill B-cell cancers by targeting their telomeres through this antibody mutation process. And you can tell that I'm a lab scientist rather than clinician, I don't have any photos of anybody in my lab. I actually don't have photos of people in my lab, so you guys are really embarrassed about that. But if we move to the last slide, so because I can't see my own slides, I'm getting ahead of myself. To the next one, sorry. That this work was done by very young students in my lab, nearly all of them PhD students or postdocs, who were all listed there over several of the last years. So thanks very much for listening.
Thank you so much. I never cease to be amazed at what is going on at the Centenary and and how relevant and wonderful is the work that you're all doing. It keeps us all inspired, and it keeps those of us who keep supporting you inspired. So thank you very much. That was truly fascinating.